So now I think we can start. It is time.
Yeah.
Very good afternoon and a hearty welcome to this Golden Jubilee Distinguished Lecture or 60th lecture that is being organized by INA Bhubaneswar chapter and our partner institutes, including IIT Bhubaneswar, Niger Bhubaneswar, IMT Bhubaneswar, SOA University, and ICT IOC Bhubaneswar campus, plus the IEEE Bhubaneswar section. And I'm really very happy, and it is a really golden opportunity for us to recall that in 21st, on 7th December 21st, we started our actually first distinguished lecture. But a long way actually we have proceeded, and now we are really having the 60th lecture today by all eminent people, not only from India, many people from abroad also have given this lecture, and it has become very, very popular. And all these lectures actually we have recorded, and with the permission of their the speakers, we can actually make it available to anybody and they are all recorded in YouTube. And here I'd like to say that today's lecture is being given by one of the actually the stalwart in chemical engineering field. Not only he is an outstanding academician, but also a very excellent person so far as actually his industry connect is concerned, and a lot of works that he has done. So today's speaker is Padma Bhushan Dr. J.B. Joshi. Padma Bhushan Dr. J.B. Joshi needs hardly any introduction, but still for his brief introduction, I will say he is currently the Chancellor of Institute of Chemical Technology, Mumbai, and also distinguished emeritus professor in Homi Bhabha National Institute. And if we see his academic credentials, he is BTech, PhD, everything from UDCT, University of Mumbai. His international publications is 661. And his citation is 30,687. H index is 86. Number of PhD thesis guided is 134. Number of postdoctoral students that he has guided is 25. And the awards actually that he has received, there are too many, but one thing actually, the few things that I would like to highlight, he is a fellow of the World Academy of Sciences. He is also an international fellow of US National Academy of Engineering. He is a Bhatnagar Prize winner in Engineering Sciences. And as per the Stanford University survey, survey placed him at the top 0.1% of engineer scientists of the world. Really commendable. And his research experience is over 52 years. His research areas are fluid mechanics, multiphase reactor design, computational fluid dynamics, atomic energy, solar energy, and bioenergy. Professor Joshi has about 50 innovations to his credit. He has developed new and novel process designs, products, and implemented in large, medium, and small scale industries. Designed almost 1,000 reactors and extensively participated in process identification. He has increased capacity, quality, and safety of more than 100 operating processes, making them globally competitive. His designs are substantially lower in capital cost and as well as operating cost and equivalent to global standards in performance. His recommended design procedures are extensively used worldwide. All the implementations are in successful commercial operation. A really notable things for all of us, and it is befitting that this technology day lecture is being the Golden Jubilee Golden Jubilee distinguished lecture is being given by Professor J.B. Joshi. Of course, he has many other things to say, including a commendable service that he is doing for the service for the society, and all these things are there in the little brochure that we have placed. Today, his talk is actually going to be prosperity through science and technology and climate change, clean energy transition, and relevance of nuclear power. So, before actually I request Professor Joshi to present his lecture, I will request one of our partner institute director who is here and who knows Professor Joshi also very well, Professor H.N. Ghosh. Please say a couple of words about your institute activities and Professor Joshi.
Thank you, Professor Acharya. Well, I know Professor J.B. Joshi from the day I heard his name when I was in cross training school and joined in chemistry department, and I know, he's a really noted chemical engineer, but he did a lot of projects in BRC, particularly with the metallurgy or material science department, the Bhava Kavach actually, which many of Indian scientists do not know. Professor Joshi was the key person, and there's a product of BRNS. I think Professor Joshi and some scientists from BRC, that the Bhava Kavach, where the bulletproof jacket produced, and it was installed with the army, and they are using actually the Bhava Kavach. So, if you talk about his academic credential, and you already told, I mean, a person of his stature with Padma Bhushan, you can understand. Very few academicians get those accolades. So, it's a very, very important person, and particularly when I met many times, I mean, I was very young, so whenever I used to meet it, and he used to tell one thing that, you will not find another institute like BRC. So, I remember that Nano Institute in Kalina campus. There was that Professor Santosh Haram was the director, and he called he organized a conference. I gave a talk, and Professor Joshi was the chairperson of my talk, and there he told that by the time I was working in Institute of Nanoscience and Technology as a director. Then he was asking like what you're doing, how do you feel? Then I was telling, well, atomic energy is atomic energy. Then he's telling that he told, I clearly remember that any research in this country can be done in the corridor of modular laboratory. You enter any laboratory, there will be expertise actually, you can get it and help, and nobody can compete with the Bhava Atomic Research Centers. So I was so happy to know, because I'm the alumni of Bhava Atomic Research Centers. And then, after completing, I came back to BRC, and I was there, and now I am here. So thank you, sir, for your inspirational words all the time. When I mean, many times in Homi Baba, to HBNI, some conference I met you, I talked to you, and you give talk, and very, very inspirational talk always. Thank you very much for accepting the invitation and enlightening us, actually. Thank you very much. Yes.
Thank you.
Professor Ghosh. May I now request Professor Joshi to please share your slides and give your distinguished lecture. We
Thank
are
you.
all eagerly waiting for it.
Yeah. Thank you, Professor Acharya and Professor Ghosh, for your kind words. In fact, I'm indeed grateful to all the academies. And now that I have completed 50 years after becoming fellow of First Academy, and it has given me all the prestige which is required in the community. So right from 1988, I'm enjoying the fellowship. My overall driving force for research and education is how to enhance the wealth of the nation. Our nation is considered to be poor on the basis of per capita income, and we rank 140th from the top or 12th from the bottom. So it is poor, and though it is poor, we are importing so many things. Crude oil, 20 lakh crores, and defense equipment, electronics equipment, most of the equipment we import. So whether we can develop technologies with the help of young boys and girls so that the preparedness of the nation improves, that is the overall objective of my life. I give lectures like this. I carve out some case studies out of the total case studies. But you can say more or less my conclusion is we are poor, we need to develop wealth, and that is possible only with the help of innovations. Our young generation is outstanding. Whatever work they are assigned, they do it so faithfully and nicely and come out with excellent ideas. So I definitely like to be with them and show them growth. So that is the overall conclusion. Our nation is endowed with so many problems which can be converted into wealth. So I'm going to tell you some of those case studies where wealth was generated. Recently, there has been sensitivity that we are importing plenty things from China, including some simple things. And why we are so, I have tried to analyze in my own way and given several test cases and case studies so that we can be much more competent than China, whatever we choose to research on. Most recently, Government of Maharashtra has assigned me 16 pharma molecules to make them economical. The total import bill is 3,000 crores. Similarly, on carbon nanotubes and graphenes, there is another 10,000 crores, 10 to 15,000 crore business that is to be converted. And one major activity in which I'm busy is design of small and micro nuclear reactors. So some of these case studies I'll mention to you, but as I told you, I will conclude saying that there are plenty of opportunities for science and technology in the nation, and there is an excellent new generation. These two things can be combined together for generating wealth for our nation. So why envy China? Let us introspect and develop rational procedures for design. Next slide. So what is that China has done? Their mindset is of capturing worldwide market. 65% of their make is exported. Cost of energy and finance both are low. Industry academia relationship have been very effective. In fact, I have many friends in China. They say that academics are considered as partners in the business. China graduates 4 lakh engineers per year. That number we have surpassed, of course. I'm close to design of equipment in chemical industry. And worldwide, chemical industry does only 1.5% of business. And this is because our cost of production is high. So if we design equipment by purely empirical methods, then the sizes which come out, the reactors and separation equipment, they get over-designed if we don't understand, resulting to high capital and operating costs, long startup times, and are difficult to troubleshoot. So I have developed a 3-point methodology. That is, if the equipment is of gas liquid type, then there are a variety of steps like dissolution. If there is a catalyst, then diffusion, external diffusion, internal diffusion, chemical reaction. So at all the points in the reactor, which one is controlling step and how the fluid mechanics in the reactor, it controls the overall operation. I'll come to that quickly. I'll take first of all one example, and then this is the hydrogenation of ethyl naphthalene, and the manufacture of hydrogen peroxide is the final product. So what we do, that is, out of the naphthalene 2 rings, if one ring is hydrogenated, then we get B. And when both the rings are hydrogenated, then we get C. B, partially hydrogenated product, can be oxidized. We get A back, and we get hydrogen peroxide. That is, B is oxidized, so that to give hydrogen peroxide and A. If you get C, C is unwanted product. These are solid particles, and they interfere with the continuous operation of hydrogen peroxide. And anyway, C is the loss. So what I was emphasizing was the mechanism and then the kinetics. That is, A going to B, what is the kinetics? B going to C, what is the kinetics? And rate controlling step. Next slide. So this was being done in a vertical bubble column reactor. As you see in the picture, there is a vertical cylindrical vessel with sieve plate at the bottom. With sieve plate at the bottom, and yeah, and the compressed hydrogen is introduced at the bottom, and when it enters through the sieve plate, then bubbles are formed. The purpose conversion of hydrogen is small because hydrogen solubility is very poor. Unreacted oxygen, to which fresh hydrogen is added, and again it is recycled. So this is the usual equipment for hydrogenation. And as I told you, we should get only single ring hydrogenation or saturation, and nothing should happen to the secondary. So when this problem had come to us for solving commercial problem, the conversion of A was 70% and yield was 70%, that is B formation, and C formation was 30%. So purpose formation of 30% and which is not useful, that was a big load to the company. Now, if we investigate the mechanism, A going to B was found to be dissolution control or mass transfer control, whereas B going to C is reaction control. When we say mass transfer control, this means all the concentration difference occurs across the film. Or if we make it mass transfer control, then concentration of hydrogen at the interface is 0, and bulk concentration is in the bulk of the gas. And if the concentration of hydrogen is 0 at the interface, there is practically no concentration of hydrogen in the bulk of the liquid, and the reaction will not occur, which is B going to C. A going to be mass transfer control. We keep it mass transfer control throughout the reactor, and when it is 0 in the liquid phase, so this was organized. So what is happening here, if we don't do that, then the catalyst particles are being suspended because of the turbulence generated by bubbles. There is a eddy diffusivity, and eddy diffusivity is responsible for dispersion. So for better dispersion of solid particles, if we increase the gas flow rate, then gas liquid mass transfer coefficient increases and B going to C reaction that increases. If we make the gas flow rate less, then the conversion is slow. So both the ways there is a problem, and by organizing exactly mass transfer control. So how that was done? As you can see, there is a external pipe like this, and it is connected at the bottom. Now in this column, we have gas liquid solid dispersion, whereas here there is a gas separation and only slurry is there. So if we take two similar points, here there is gas liquid solid dispersion, whereas here there is only solid liquid dispersion. And obviously the density of gas, particularly that of hydrogen, is very low, and therefore overall density on this side is less than overall density here, and therefore static pressure rho gh is less at such points as compared to rho gh at such points. So we get driving force, and liquid flow starts from the bottom, it goes up, it goes down, and the circulation velocity obviously depends upon how much delta rho we have been able to keep. The most important point is, earlier we wanted the making of bubbles for the suspension of particles. Now that job has been withdrawn from gas bubbles, and a flow of liquid after circulation, that is suspending particles. And we adjust the delta rho in such a way that the liquid circulation is sufficient for solid suspension. So job is withdrawn from the gas phase and given to the liquid phase. And when the upflow of liquid and downflow of solids, the settling velocity of solids, they become equal, the concentration of particles also become equal. So we pass exactly that gas flow rate, which is equivalent to the gas film controlled operation. So rate of mass transfer is, say, approximately 10 times less than the rate of reaction. And we adjust the conditions that the add sufficient catalyst for 100% conversion and 100% selectivity. And the company is operating plant now almost more than 25 years with 100% conversion and 100% selectivity. So this is the one test case study. So this is a slide I have incorporated for this gas liquid mass transfer. If we don't do our own homework, then there are empirical correlations, 16 correlations, and their predictions is compared with whatever are the literature experimental values. There are approximately 2,000, and you can see points anywhere. So the point to be emphasized here is you cannot believe any value. Any value. It can be as low as 0.1. It can be as 0.9 or point more than 0.9. Therefore, we have established a rational procedure for design, which briefly depends upon the understanding of fluid mechanics in the reactors and chemical reactions in the reactor. So we do in the following manner. First of all, for multi-phase system like gas liquid, liquid liquid, gas liquid solid, gas liquid liquid, we first of all find the mechanism and kinetics of a single phase as well as multi-phase reactions. Then in the reactor, we understand the flow using flow visualization, particle image velocimetry or laser Doppler velocimetry, ultrasound anemometry or tomography and tomographic studies. We do gamma ray tomography on the commercial equipment as well. Then we do detailed computational fluid dynamics for all kinds of multi-phase systems, single phase as well as gas liquid, liquid liquid, solid liquid, gas liquid solid dispersions. The next step is, see, while we make measurements, the measurement techniques, they have certain assumptions. Similarly, computational fluid dynamics also has assumptions. So in order to go further with confidence, we really validate both the measurement as well as fluid mechanics, the measured fluid mechanics, so that the safety simulations, they become validated. Then the bubble size distribution, phase holdup, effective interfacial area, all those can be calculated with the validated computational fluid dynamics. We also use artificial intelligence. That is, we definitely start the plant first, try to get data, we reprocess the data and keep on optimizing further. And then there is of course, implementation. So such types of hydrogen peroxide reactors where column type of hydrogenation is involved, we have done it at more than 50 places. There is another hydrogenation which is done in stirred tanks. That is, hydrogen is sparged from the bottom and that gas phase is broken into bubbles and also distributed throughout the equipment by the motion of impellers. The catalytic hydrogenation, like say for example, para-nitrophenol to para-aminophenol, the raw material for paracetamol, was being made by hydrogenation in the presence of iron filings and hydrochloric acid. That is, in a say 5,000 liter reactor, about 1,000 kilos of iron filings were taken, 1 ton of para-nitrophenol was added, and hydrochloric acid was slowly added, so that the nascent hydrogen formed because of the reaction between iron and hydrochloric acid, it was hydrogenating the para-nitrophenol. There were plenty problems. One problem was with the product 1 kilo, 5 kilos of waste material, solid material was forming. And it was trapping about 10% of the product. So both were losses. Secondly, the amino compounds are carcinogenic, and taking care of 5 kilograms per kilogram of product, it was a very big task, close to impossible task. So in the literature, the hydrogenation using hydrogen gas and catalyst, that is reported. And when such a reactor was designed, as shown in the picture, with impeller and vessel, it was taking 7-8 days for hydrogenation with the gas. And a lot of gas was accumulating and there was no way to recirculate the gas. And reactors were known in Germany and Switzerland to complete the reaction in 3 hours or 4 hours or 2 hours, depending upon the need of the operation. So when we inquired the cost of hydrogenator, for 2-ton hydrogenation, the cost quoted was 10 crores. Now, at such a high capital cost, we cannot make our business competitive. So it has to be brought down. So as I mentioned at the beginning, we importing all kind of equipment in fertilizer industry, in petroleum industry, in pharma industry, in paint, varnishes, food industry. We are importing a huge amount. So we wanted to find a solution to this. So we spent approximately 3 years and came out with the design of new reactor. As you can see, the impeller is now surrounded by a stator and there is an opening for hydrogen going into the reactor. So when impeller rotates, we know Bernoulli's principle, the kinetic energy here enhances. And we know that at same location, the kinetic energy plus pressure energy is, the summation is the same. So when we increase the kinetic energy, we get pressure reduction at such locations. What is otherwise the pressure here is rho GH. Pressure here is rho GH. But when pressure reduction is here more than rho GH, then gas can enter. There is a nice path for hydrogen, and pressure here is less than the pressure here. Rho GH is overcome by the kinetic energy. So we implemented this in late 80s for 2-ton reactor, and the reactor was made in 12 lakh rupees instead of 10 crores. We have saved thousands and thousands of crores for the nation, but I'm going to tell you only some examples. So such equipment can disperse the gas as shown here only in the top reactor. So bottom up of the reactor is free of the gas and is not active. So for making it active, we provided another impeller, and this another impeller, the job was that this induced gas was to be distributed throughout the liquid. And one more impeller was required for solid suspension, and this equipment is now implemented. In the literature, there are many self-inducing impellers, particularly in the flotation industry. But whatever we had done at the beginning, we were somewhere here 1 or 2 liters per second, but research was required for a given power consumption, how to reduce the pressure. Minimum 50 liters was required per second, but now with the understanding of fluid mechanics, pressure reduction, and hydrogen suction, we can go now even up to 200 liters per second. I'm taking another example of air oxidation. Typically, if we see internationally, even if we buy international technology, I was participant in one US activity of Department of Commerce, that chemical industry is quite expensive. That is, capital costs are high, operating costs are high, whether we can bring them down. So approximately 10-15 years ago, they had a mission to reduce the capital and operating cost. I'm not talking about India. This is an international mission. So I was also participating, and we in India developed 3 technologies in this direction. See again bubble column reactor, see plate at the bottom, and this is air oxidation. So liquid is countercurrently flowing, whereas gas is flowing upwards. So this equipment was designed, and this air oxidation is required in paper pulp industry. So since the liquid phase was completely backmixed, we know in chemical engineering that the volume of the reactor is very high volume, whereas if you have a plug flow behavior, the volume is the least from mixing point of view. Therefore, we tried to make it plug flow with the help of multiple stages, and this is called sectionalized bubble column. We designed one more. The principle I have said earlier, that is the liquid circulation arising out of pressure driving force. Now, initially gases pass from here, and the gas liquid dispersion is separated, and only liquid overflows from here, liquid goes down. So the liquid circulation is started with the help of upflow bubbles, and when liquid circulation is stronger than bubble rise velocity, then we can introduce gas phase in the side also. The bubbles now go down and go up. What is important? Here gases are in the part of the reactor. Here the gases are throughout the reactor. So therefore, rho GH at the bottom here has to be less than rho GH at the bottom here, so that we get pressure driving force, and liquid circulation so generated permits the introduction of gas at such locations. So this we developed, and we wanted 50% reduction. You can say that we have bubble column, then bubble column, liquid phase disperse, sectional as a bubble column, and external loop airlift reactor, which I mentioned to you. So 51 meter cube, 51 kilowatts were required for conventional bubble column, and for external bubble column reactor, it is 26. So operating cost is half, and the capital cost is also less by the volume is 50% less, and therefore the cost is also 50% less. There is one example, international example, making by the methanol by fermentation. We get natural gas and oxygen and make methanol. With carbon monoxide and more hydrogen, this is with oxygen, with hydrogen, we can get methanol. Carbon monoxide plus 3 hydrogen, all these reactions are possible, and it is also possible to reduce carbon dioxide with hydrogen to get methanol or higher alcohols. The reaction is a biological reaction. Dissolution is mass transfer controlled. Now, when this reactor had come for design, they had two important restrictions. One is the price of the reactor should not be more than $10,000 per meter cube, and operating costs per liter of methanol should not be more than 15 cents. So now the new reactor which we developed for the catalytic oxidation, the same reactor was used in this case, and a successful commercial plant is now operating for this fermentation. There is another gas liquid reactor in the A plus B means B is oxygen in the air. We need the desired product A going to B, but we get intermediate products. This is paraxylene. So when paraxylene, both the CH3s are converted to COOH, we get terphthalic acid. Otherwise, we get intermediate products. This is because this is a radical reaction, and if we get paraxylene radical, and if it is not oxidized, if oxygen is not nearby, then two paraxylene radicals, they connect, and we get a dimer. And in the similar manner, you can get trimer, etc. So dimer, trimer, the color of the product then becomes, in the presence of these products, either yellow or brown or black, so which is not required. So there was a certain capacity and the product was the up spec. And therefore we wanted to solve this problem. A plus B, both the CH3 groups are to be oxidized. A plus B going intermediate products means the partially oxidized products, or A plus B byproducts means these dimers, trimers, tetramers, etc. So we understood this, and in the earlier case, we had to design the oxidation in such a way, as well as in another case, the hydrogenation in such a way that interface hydrogen concentration becomes zero, and therefore bulk concentration is zero. Here in this case, reverse was the case. That is, lot of oxygen is required in the bulk in the vicinity of the radical to kill the radical for making the terephthalic acid. But that was not happening, and therefore we getting upspec products and capacity was also low. The another problem was with paraxylene, acetic acid is used as a solvent. So when the paraxylene gets oxidized, the acetic acid also gets oxidized, and we get consumption of acetic acid 80 kgs per ton of product. Then when we provided good amount of oxygen in the liquid, we could reduce the catalyst loading, we could reduce the temperature. Because of that, oxidation of acetic acid has been reduced from 100 kgs to 90 kgs to 80 kgs. It is wavering now between 30 and 40 kgs. So, and this now overall technology has been implemented throughout the world. So I'm giving several test cases. This is from froth flotation. We know that there are hydrophilic particles and hydrophobic particles, and the bubbles are made by self-induction here. And when bubbles rise, the bubbles and particles, they collide with each other. If there are hydrophilic particles, the hydrophobic particles, the particles attach to the bubbles, and we get scam here, which can be removed. So for getting particles together, turbulence in the liquid is required. But if there is a right turbulence, then they can come together. And if there is an intense turbulence, then detachment occurs. So in the vicinity of impeller, the turbulence is very high, and near the wall it is very low. And therefore, some attachment occurs in the impeller region, and attachment does not occur near the wall, but whatever attachment occurs, the detachment also occurs. So what we want, homogeneous and isotropic turbulence throughout the liquid of the desired intensity and scale, which can be done by a fluidized bed. You select the particles and particle settling velocity in such a way that you get homogeneous and isotropic turbulence. This we proved with the help of measurements, that is laser Doppler anemometry. When spherical particles were employed, then we got the isotropy was not there. The actual intensity was 1.4 times than the radial. But when we suspended such paraboloid type of particles, then the lift of the particles, they helped in generating turbulence in the horizontal direction, transverse direction, and we got practically isotropy. And this equipment is operating. What is the result? If we take, say, 10 kilowatt as power consumption, by flotation machine, the recovery was 0.6. So 0.4 was not recovered. So another flotation machine, 0.6 of 0.4. So normally 4 or 5 flotation machines in series are required. But if you do with isotropic turbulence, you get close to 90% in the first cell. And no moving parts, it is a column type of operation. We have developed a technology for chromatographic separation. We found that what is most important is liquid distribution. All particles, they are experiencing exactly the same quality of fluid mechanics. So this is a fractal type of distributor. This is the inlet. It distributes into 2, then distributes into 4, then 8 and 16 and 32 and 64. So what do I mean by the uniformity? If we take furthest point here, at the end of each red bar, hole is drilled and gas enters only through this, and then it distributes. So suppose we take this as a furthest point, then gas goes here 1, 2, 3, 4, 5, 6. This is the furthest point. 6, this is the furthest point. If you take closer point to this, then also gas has to pass through 1, 2, 3, 4, 5, 6. So the resistances experienced for gas path at any point is identical, and therefore we could design the commercial chromatographic separation. Dr. Ghosh mentioned about carbon nanoparticles and Baba Kavach, bulletproof jacket. Thanks to, I have been thanking BRC in many ways. Professor Ghosh, he told one experience, but what I say is it is a heaven. With whatever equipment you want in the world, it is there. And whatever expertise you want of any type, it is there. So you can produce so many things, and I had an opportunity in the last 16 years to do at least five innovations and implement them. So I wanted carbon nanotubes for making the noble metal catalyst in place of the usual activated carbon. And I needed about 10 grams of carbon nanotubes, and inquired in the US market. They quoted $50 per gram. $50 per gram. I am repeating again, $50 per 1 gram. China was cheaper. They quoted $10 per gram. $10 per gram. For the 10 gram quantity, that is either $50, that is $500, or $50. That money was there with me. $50 is no problem. But I felt something awkward that to pay this much money outside and then do the research, I did not feel comfortable. And therefore, with the help of scientists and young PhD students, we started developing this technology. Again, the mechanism is the same. Understand fluid mechanics, do computational fluid dynamics, understand the rate controlling step, and try to optimize what is desired for optimizing the mechanism. That 8-point step is there. So we developed a fluidized bed reactor, and we saw to it that the conversion of the gas from inlet to outlet, this is the problem being faced throughout the world. We saw to it that more than 90% conversion is there. And the purification of the product, also we developed some novel procedures. And it was important that below 800 degrees centigrade, it was reaction controlled, and above 800 degrees centigrade, it was diffusion controlled for the catalyst particles we had taken. So it used to take, for making about in laboratory 10 grams, it used to take 2 hours. So that was too high from capital cost point of view. And any rise in temperature will not give increase in the rate of reaction beyond 800 degrees because it was anyway diffusion control. So we reduced the catalyst particle size and made them nanoparticles, and totally eliminated the diffusion possibility. And we went to 1200 degrees centigrade, and 2 grams or even, that is, the residence time was of the order of 2-3 seconds. So this is a continuous reactor. Yeah, the raw materials are entering this way. This is the 1200 degrees centigrade with 2 seconds residence time. There is a separation of argon, and there is a product. This I want to emphasize. That is, I was quoted $50 per gram, and I have now implemented at 2 locations 60 kgs per day and 1 ton per day. The cost of production at a location of 16 kgs per day is $25. $25. And if it make 1 ton per day, it is $20. I'm repeating, $25 per kilogram. Per gram, it is some 2.5 cents or some of that order. And this technology is implemented. Then with the help of this, there were 2 boys and 2 girls. They made a composite using ultra high molecular weight polyethylene and stitched bulletproof jackets. And as I told you earlier, BRC officers and directors of individual groups, they are very powerful. They contacted the defense and requested them to test the validity of the jackets. And they cleared 100%. None was defective. So they sent to police department. And our own Honorable Prime Minister, he announced in the Parliament, now we have a technology and now onwards we shall not import. So huge quantity is made by a Tata Group company in Bangalore and Midhani Mishra Dhatu Nigam, a government company in Hyderabad. And we are going to transfer technology one to private industry who will manufacture in big way. We have developed graphene technology also. We have developed the graphene composites for increasing the blade length in the wind energy. Calculations show that if 80 meter the length of the fan is increased to 200, then at the same location we will be able to capture, instead of 1 megawatt, the 8 megawatt. And the result is very encouraging. We will implement it now. Similarly, graphene concrete composite, that has also shown very good results. This is the pyrolysis. We get huge agricultural waste. As shown here, we get crop residue of 600 million tons. And it is burned right now in most of the cases. And we here in the months of November, December, pollution not only in Delhi, throughout the country. So instead of burning, we have developed pyrolysis, gasification, and the production of biohydrogen. We have been sanctioned total approximately 40 crores for developing the demonstration plant for this. So we have done it for a variety of biomasses, at least 50 types of biomasses. Now we have been told to do with the coconut shells and also cashew nut shells and bamboo. So that work is ongoing in a big way. So suppose you take cluster of 5 villages, then population total is 25,000. Land with 5 villages. Here what I have done, I know the total land of India. I drawn a grid of the land 5,000 hectares. So in which on an average there are 5 villages and population is 25,000 and extra biomass is 50,000. Please note what I have done. I know total biomass of the nation. I know total land of we leave the water bodies, we leave the mountains, we need the urban areas, village areas, and whatever area remains, this is for establishing a business case. So increase in productivity, I have done 25%. I have got even up to 100%. So if the land is already fertile, it can be more fertile by 25%. But if it is not fertile, then we can do it by 100%. I have done these calculations. Maybe I will not go into the details, but the point is the payout period is 2.4 crores and the total number of jobs increased in the nation are 16 million. And we can get 1250 million ton oil equivalent. This is much more than what is the total energy consumed in India. So it is a big source of energy, good employment, and I'm trying to convert this into a cooperative society so that the capital cost, per capita income of the local people increases by a factor of 2. And if you go to the villages in any direction, you find plenty opportunities. I don't know, I have one of those cases, the combustion is 28% of the energy is wasted in cooking type of application. And the World Health Organization tells that we should have only 1 or 2 particles per meter cube. But in our Indian kitchens, we have 500. Sometimes there are 5,000 particles. And 16 million the household ladies, as well as the small children in their lap, they die everywhere. Such an intense problem is there, and this problem we have tried to address. And it reduces carbon dioxide by 1 gigaton. As a nation, we need to reduce by 5 gigatons, and of which 1 gigaton can be taken care of by CO2 reduction in kitchens. The subject of climate change is known to all we academicians. Now here, what I have tried to show, I'll try to finish it fairly quickly. What I have tried to show, of course, here there are plenty news items which make us fearful. What is going to happen in Mumbai, what is going to happen to Orissa and Bengal, and these news items keep on coming. We know that why the global warming comes. All the bodies, they radiate, we know. And the wavelength of radiation decreases as the temperature of the body increases. So whatever we get from the sun is a very small wavelength, visible length radiation which comes up to the nation from the earth. India being at much lower temperature than the sun, this is low frequency but long wavelength. And when these green gases, they accumulate in the atmosphere, this high wavelength energy is unable to get radiated, whereas low size of the energy from the sun, it can appear. So there is a net difference, what Earth gets and what Earth radiates. The balance remains with the Earth, and we call it as a global warming. We know that these are the carbon dioxide, methane, nitrous oxide, fluorine gases. These are responsible. China emits the maximum, United States for CO2. These 2-3 slides, I'll go very fast. This is the important point. The CO2 emissions in gigatons over the years from 1750, that is our industrial revolution, has gone from 200 ppm to almost to 420. It has become almost double. So all of us know that Japanese scientist Sukuro Manabe, he did on a piece of paper that if this carbon dioxide concentration in the atmosphere increases by factor of 2, then our Earth will become warm by 2.28 degrees. And if that concentration is made half, then it will cool by 2.28 degrees. We know that the scientist got a Nobel Award for his predictions. So all of us are trying for zero carbon emissions. So the India's nationally determined contributions, these are to reduce the emission intensity per GDP by 33 to 35%, 40% fossil-free power generation, and creation of additional carbon sink equivalent to 2.2 to 3 billion tons. So what is that we have promised? What we have promised is India will reach, our Prime Minister has promised, its non-fossil energy capacity by 500 gigawatt by 2030. India will meet 50% of its energy. India will reduce the total projected carbon emission by 1 billion. By 2030, India will reduce the carbon intensity. So this has been promised by our nation, and we all engineers, we have that responsibility. And what it says, that if we don't act, then carbon credit will reduce our business by 7.14 lakh crores. But if we do it, our business will increase by 2.9 lakh crores. This is very interesting. That is, as the economy improves, the energy requirement is proportional, directly proportional. And right now ours is 3.5 trillion economy, and we have installed capacity of energy 10,000 terawatt hours, 10,000 terawatt hours. We wish to go to 35 trillion economy, and therefore we want about 55,000. From 10,000, we need to go 5 times in terms of energy. But the fact is that if we implement all solar projects, photovoltaics, solar thermal, all wind projects, all hydro projects, we are going to get 4,000. Presently, we have 10,000. This is 4,000, and we need 50,000. So only option is nuclear energy, and our university has taken a big program, big center on design of SMRs and MMRs, small nuclear reactors and micro nuclear reactors. And tomorrow we are opening the center. Honorable Dr. Kaporkar, he used to be president of our academy. He will inaugurate the center. So here is the fuel. Here is the fuel. Water in the vicinity becomes high. Then steam is liberated, water is cooled. You have delta T, you have delta rho, and therefore there is a liquid circulation. We maintain the liquid circulation in such a way that the heat flux is maintained properly. So a lot of computer simulations are happening, and we will also have a demonstration equipment. The economic advantages are, of course, internationally the cost being said is 50 crores to 100 crores. We wish to make in between 10 to 15 crores. Because of small plant investment, a large number of investors would like to invest in the large expansion of the nuclear power program. Reduction in interest during construction. Usually large size reactors take 7 to 8 years, and the capital cost goes away, 50% goes away during construction period. And because of short construction period, which is factory assembled, the IDC is much less than large reactors. Make in India, all components of the new reactors can be manufactured in India. So several hundreds of such reactors can be built. We not only boom the Indian manufacturing and service industry, but also help in reducing the present unemployment. I come to the conclusion, which I said at the beginning, the Indian production costs are only 10 to 15% higher than the Chinese costs. And I have shown you 3 examples at least, where the capital costs and operating costs can be reduced by 50% each, and we can become competitive, not only with China, but in the world. And because these costs are higher, we are importing worth 24 lakh crore worth chemicals. We are buying our edible oils, which are 8,000 crores. It is clear that our nation is still financially dependent. So we got a political freedom in 1947. But till today, we are not independent nation. We buy about 24 lakh crore, which is a major portion of our per capita income. And we need to start another freedom motion, the economic freedom motion, though we have won the political freedom motion. I emphasize the importance of insights. for bringing the cost down, are internationally competitive. The global warming has already arrived and net zero carbon is a necessity. The favorable option appears to be small and micromodular reactors. I'll be very happy to answer any question. Thank you for giving me the opportunity.
Thank you so much, Professor Joshi.
Yeah.
Now, actually, it is open for certain questions and answer. Please really ask your things.
This is DP Mishra. Can I ask?
Yes, yes, nice to hear your voice.
Dr. Joshi, it was absolutely inspiring lecture, and people as old as me, I am inspired to work in your area and and do something concrete about it. Just my question is small with regard to the SMR and the atomic the reactors. The entrepreneurs have to get clearance from Atomic Energy Regulatory Board, like any of the atomic reactors.
Yes, 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 yes. Yeah, but it is forthcoming, as you know. That slide I should have kept. What is the different initiatives central government is taking? The government has kept 20,000 crores, and they are going to build 50 gigawatt plants up to 2050. So that much money they have kept aside. Plus for research and development, 20,000 crores. The Atomic Power Act is also under revision. Right now, if you build that reactor with the help of ICT technology, the fuel you will have to buy from a party which is approved by the nation. But the law is being changed, and that will also come in private. So all the fuels we have identified, who can manufacture, who are certified, and then we are waiting for change in Atomic Energy Act as well.
But India recently signed some agreement with USA for these small modular reactors, right?
Means that is a sort of in overall activity. Suppose we want installed modular reactors, 1, 2, or 1,000. That agreement doesn't touch even 1%. They have not agreed to give the technology of small and micro modular reactors. Or if at all they give, they will give per megawatt 40 crores, 50 crores.
But in the ICT reactor, what will be the fuel actually?
Thorium.
Thorium. That is, we have got a lot of stockpile of monazites at different places.
Yeah, which is sufficient for at least 500 years.
Yeah, I know.
With
Indian rare earths in
function
Odisha.
of 50,000 terawatt hours, we have a deposition of 500 for 500 years. And I'm sure we will find another deposits.
Yeah. Thank you very much, Dr. Joshi.
Thank you. Thank you.
Sanat Kumar ji, would you like to ask some questions?
Yes, Dr. Dr. Acharya. I feel too small to be able to ask a question of Professor Joshi or Ghosh. But anyway, for their information, I may say that I am from the 6th batch of training school. There's one. But it so happens I'm not a chemical engineer. I was born in BRC, then went on to NPCIL. I retired superannuated as executive director in NPCIL. That is my background. But I am a mechanical engineer trying very, very hard to do what you have said, make everything in India. That has been my thing also, and I have, in my own small way, I have been successful. But certainly, chemical engineering is not my field at all. So I am in no way to ask you a question on that. I am interested in giving my opinions about that SMRs that you are talking about. Okay, I'm
Yeah.
basically a nuclear engineer, so I have views, and
Yeah.
right away I will place my cards on the table. I am
Yeah.
against SMRs, fundamentally against SMRs. That's not right.
Okay.
India should
Yeah.
not be going for that. This is my view. Of course, it is a view, and free speech, etc., are there. I'm not blaming anybody, but I think I would like to caution you, if you are working on it, kindly try to keep these aspects, which I'm going to tell you one or two, in your mind and try to oppose. And if, of course, if you are overcoming that, I have no problem. First of all, thorium is not a fuel. You cannot have fission. You can have fast fission with thorium. You cannot have thorium per se is not a fuel. You have to convert thorium into uranium-233. Only then it will cause a fission. But you have said you are going to use pressurized light water reactors. Okay, so that is point number one. Point number two is that in order for the type of reactors that you are trying to design, that is pressurized light water reactors, there are two. Any reactor physicist, if you're going to ask, the smaller you make the core in order to make, the greater is the escape of neutrons. You need neutrons to be able to cause chain reaction. So a
That's
small
right.
reactor
That's
like
right.
this is wasteful of neutrons, which is what we want to convert thorium into uranium-233. We want neutron, and neutrons. So this small reactors will eat neutrons fundamentally. Therefore, what you need is enriched uranium. Now, enriched uranium, yes, in India we can make enriched uranium for strategic purposes. If you are going to build 300 or 400 SMRs like this, it will be very difficult and you will have to import. Importing that fuel is fundamentally against anything. I see Dr. Baba's photo in Dr. Joshi's room. So he said no import. So if you want to follow Dr. Baba, we should try to do. So I am suggesting that these aspects, I'm sure Kakodkar is aware of it, very much aware of it. He is much better than I am, so he would be aware of it. So you keep this in mind. Lastly, I've recently only read this. These small reactors are so small. Okay, so now let us say you put a hell of a lot of enriched uranium, and they operate for 18 months or 20 months or 24 months. But they are so small that you cannot do maintenance. Supposing you have a pump, the pump requires some change, bearing change or something like that, or valve. They are so small, you cannot do. So what they are saying is, we will take out the reactor, throw it away, and put a new reactor, which is ridiculous, absolutely ridiculous. This is what they are trying to say. I'm sorry I have used very strong words, so please excuse me for that, but I am a strong opposer of these small reactors. Thank you.
Yeah, yeah. I'll keep your points in mind and examine critically. We will introspect critically and try to overcome. But I'm sure you will be available to give your opinions.
Yeah,
We may-
I would suggest that you discuss these points with Dr. Kakodkar. He will
Okay.
be aware of it. He will tell you Sanat Kumar is wrong. He will very well tell you that also. He knows me very well. So he can tell you very well clearly Sanat Kumar is wrong, which I don't mind. I don't mind being wrong. It was just an opinion. That's all. Thank you.
Yeah. Is it possible for you to write on a piece of paper so that I don't miss any
No, sir.
word?
No. If any of you is in Bombay, you're welcome to my house. I don't want to write a paper.
You live in Mumbai?
Yes, I am in Bombay. I am in New Bombay. So Dr. Acharya knows my address. But if you want my address or my email ID, I will give it to you also. No problem. I will any day happy for you to come to my house. The problem is, if you get me talking, I won't stop. That is the issue. That is the issue. So please do come. I will be very happy to talk to you. That will get my mind off also on this problem.
Thank you.
I am a PHWR fellow, fundamentally pressurized heavy water fellow, can do reactor, on power refueling. This is my area. So anybody coming against it, I will be against. Thank you.
Sure. It is good to have all the views from all the directions. Then only progress is there. So I will honor all your opinions and try to take them into account.
Certainly,
As a part of
it's a great mistake to import this reactor from Holtec, America. You have the technology to make it. Why do you want to import? This is ridiculous. It should not be done. Thank you. You have the technology.
Thank you.
Professor Ghosh, would you like to add something?
No, I'm fine. Actually.
Okay. Any other question?
Yeah, Dr. Joshi, DP Mishra again.
Yeah.
Actually, India has got another source for uranium as the fuel, and atomic energy has got the technology, that is extraction of uranium from phosphoric acid.
Yeah.
And we have the largest plant in the world on phosphoric acid in Paradip in Orissa, 3,000 tons per day of P2O5. And when this plant was being built, there was a agreement between Oswald Chemicals and Atomic Energy. Dr. Chidambaram was the chairman, and to go with this, to have this plant in place. But somehow it has not happened actually. But that is one source which is available to India for manufacture of uranium from phosphoric acid.
Coincidentally, Dr. Ghosh, the technology development, I was responsible.
Dr.
And
Singh was,
particularly for that is
Dr.
the heavy water board was given the overall responsibility, and I enter into technology development, and the principal component was in how much short time you can extract being radioactive. So not more than 2 seconds, and so the extraction and solid particles, they should be contact for 2 seconds and separated from each other. So that equipment we developed. Again, we made the 50 tons per day phosphate rock processing per day in 50 lakh rupees. And the France had quoted 50 crores of rupees. So that equipment is done. I'll try to find, I have friends in the heavy water board. This 50 tons per day is operational in RCF Mumbai. But why they are not scaling up further, that I'll try to find out.
In fact, my company, I was working for a French company called Krebs, and that did the phosphoric acid plant from uranium, uranium from phosphoric acid for atomic energy of France actually. And so I have been excited since that time, and I built this phosphoric acid plant in Paradip, which is now being run by IFCO, and this is the world's largest phosphoric acid plant, 3,000 tons per day P2O5.
I'll take it forward again. I'll talk to the right persons. I know heavy water people. I will. I'll be very happy to meet them. They will be also happy to meet me. So I'll contact them to the present. Our Vice Chancellor of HBNI comes from Heavy Water Board. So Kamachi Mudli. And I will have a word with you.
Thank you very much.
Thank you.
It is actually such an exciting lecture. And fortunately, actually, the two persons who have interacted with you, sir, they are all from Bombay. So I think together you could really think of actually what big thing could come up. So we are so delighted to listen to you. Now I'll request Professor Renu Sharma to please propose a vote of thanks.
Okay, I have a point to.
Oh, please.
Hello, sir, Professor Joshi. I
Yeah.
have open invitation to you to Nizar, Bhubaneswar, Odisha. Please let me know whenever you are free. It is like sometimes we want to see you in our campus physically and give some talk, because I have listened so many talks from you.
Yeah.
So this open invitation, and I'll communicate to you, and I'll find a suitable time. And also I'll request that time Professor Acharya, you should come there. We can have some time here. Yeah.
Very nice. Very nice. I will also love to come. Your
Yes, sir.
NICER is doing such a wonderful job of education, educating the new generation. I'll be very happy.
Yes, sir. Thank you.
Thank you, sir. Good evening on behalf of INA Bhubaneswar chapter and our esteemed co-host, Shikshanusandhan
You're not
Jubilee
audible.
University. I'm audible, sir?
Yeah,
Okay.
audible to me at least.
Now-
Yeah.
So, thank you, sir. So, on behalf of our co-host, Shikshanusandhan University, CSR IMMT Bhubaneswar, IIT Bhubaneswar, NICER Bhubaneswar, and ICU Bhubaneswar, ICT Bhubaneswar, and IEEE Bhubaneswar section, it is my privilege and honor to propose the vote of thanks for today's 60th distinguished lecture is going on in impactful series. We are deeply grateful to Professor G.B. Joshi, sir, Chancellor of Institute of Chemical Technology, Mumbai, for delivering his inspiring and visionary talk on prosperity through science and technology and climate change, clean energy transitions, and relevance of nuclear power. Sir, your thoughts provoking insight into sustainable prosperity, the challenges of climate change, and the pivotal role of nuclear energy in clean energy transition have left us all enlightened and enriched. Sir, your lifelong contributions to science, engineering continue to shape generations, and today's lecture added another feather to this illustrious journey. We would like to thank your time, wisdom, generosity in sharing your experience with us, sir. And I would also like to extend my heartfelt thanks to the leadership and the members of INA Bhubaneswar chapter for their constant support and vision in organizing this series. I sincerely appreciate all the partner institutes, as I said earlier, for their collaborations and seamless coordinations. A special thank to all the distinguished participants, faculty members, students, and invitees, those who have joined here. Esteemed fellow INAs, sir, your presence and engagement made this session more meaningful and insightful. With this, I would like to conclude today's lecture and thank once again Padma Vibhushan Sri G.B. Joshi sir for joining us this distinguished lecture series and making our day. Stay safe, stay inspired, and thank you all. Namaste. Thank you so much.
Professor Joshi,
Thank
just I forgot, this lecture has been recorded. Can we really share with others?
Yes, yes, yes.
So with your permission, actually, we'll share it with others. And
Yeah, yeah.
also, as a token of appreciation, we'll send you a small gift. Very, very small gift, very basically a very poor organization, but we'll definitely do something. Okay.
No, no, no. My granddaughters, they will love it.
Thank you.
They really, they are very much interested in opening the packet.
Thank you.
Thank you.
Okay.
Thank you.
Thank you.
Thank you very much.
Thanks.
Thank you and good night to all of you.
Good night.